So now that we have explored polynomial functions, we are officially ready to transition to rational functions, which are ratios of polynomials. So we say that a function f is a rational function if it's defined as follows. So we say that a function is rational if it's defined in the form f of x is equal to p of x by q of x. And this is where both p and q are polynomial functions. And of course, the function in the denominator, q of x, cannot be equal to 0 because division by 0 does not exist. Now, in order to analyze the graphs of rational functions, we're going to need to consider how the graph is behaving as x approaches positive infinity and as x approaches negative infinity, aka the end behavior of the graph. And we're also going to need to consider how the graph is behaving as x is approaching undefined values, or undefined values of the domain. So to help us with this analysis, let's establish some new infinite notation for rational functions. So for analyzing graph's behavior at undefined values in its domain, we have the following left and right infinite notation. So we have that x is approaching c from the right. With this, we have a little plus symbol in our exponent here. So this is x is approaching a constant c from the right-hand side, but x can never equal c. And similarly, this new notation says that x is approaching c from the left-hand side. And again, x can approach and get infinitely close from the left, but it can never equal c. So this is the infinite notation we're going to be using for those undefined values. Now, similar to polynomial functions, we have the following. So thinking back to the end behavior of polynomial functions, we recognize this as x is approaching positive infinity. Or in other words, the x values are growing in a positive direction without bound. And again, recognizing this last infinite term from the end behavior of polynomial functions, we know that this reads x is approaching negative infinity. So in other words, the x values are decreasing without bound. So now that we have established this new infinite notation and reminded ourselves of other infinite notation, let's go ahead and apply this to analyzing the graph of a familiar rational function, the reciprocal function. So let's now consider the graph of the reciprocal function, y or f of x is equal to 1 by x. And we want to use this familiar reciprocal function to help us in analyzing the behavior of the graph of a rational function as x is approaching any undefined values, as well as the end behavior of this function. So let's first consider the behavior as the graph is approaching undefined values. Now, from the domain of a rational function, we know that x could be any real number here except 0. And that's because division by 0 does not exist. So notice the y-axis in this case is representing the vertical line x is equaling 0. And observe here, as x is approaching 0 from both sides, the graph is going to get infinitely close but never cross. So using our new infinite notation, we can observe on the right-hand side that as x is approaching 0, or approaching the y-axis from the right, the corresponding y values are growing without bound or approaching positive infinity. And very similarly, on the left, we can observe that as x is approaching 0 from the left-hand side, the corresponding y values are decreasing without bound. So when we approach an undefined value from the left and the right, and the y values are increasing infinitely or decreasing infinitely, we say that this line that we're approaching is a vertical asymptote. So now that we've observed how the graph is behaving at an undefined value, let's consider how the ends of the graph are behaving. So from polynomial functions, we know that to determine the end behavior of the graph, we need to consider what the y values are doing as x is approaching positive infinity and as x is approaching negative infinity. So coming over to our graph, we can see that as x approaches positive infinity and as x approaches negative infinity, the y values are approaching that x-axis, but they're never crossing. So using our new infinite notation, we can see here that as x is approaching positive infinity, the y values are approaching the x-axis but never crossing. And very similarly, on the left, we can observe here that as x is approaching negative infinity, the y values are also approaching that x-axis or approaching y equals 0, but never crossing. So when the y values of a function are approaching that same constant value as x grows without bound in a positive direction and in a negative direction, we say that that y value is a horizontal asymptote. So now that we have explored these ideas of vertical asymptotes and horizontal asymptotes using a familiar reciprocal function, let's go ahead and explore how we could do these or how we could apply this analysis to any rational function.